Hello, good people. We're back. We're starting the next section, and I told you that I wanted to pair these two 610 and 612 together because they're giving us techniques of doing some antiderivatives, but especially antiderivatives where I have a rational function, right? Where I have something over something. And so what we're going to do in this set of videos is we're going to do something called partial fraction decomposition. And it looks a little daunting when you look at the explanation here. But all this is saying is whenever I have a rational function, a rational setup, a fractional setup, I can break this into little rational functions that we're adding together, as long as the denominators are factors of q of x. So if I can somehow factor q of x, and we're going to factor using only linear factors, but if I can factor q of x into linear factors, I can write this out as a over the first factor, and let's call this a1, plus, no, you know what, let's call it a, plus b over the second factor, plus c over the third factor, and so on and so forth. Plus dot dot dot, and we'll just say, I don't know, n over a sub n of x plus b sub n. So the idea is this: whenever I have a fractional setup, a rational setup, I can break that into little fractions whose denominators are factors of the bottom. And so I'm going to jump right into it so you can see how this process is going to work. So again, the whole point here is we're trying to take this complicated looking thing. I don't know how to find the antiderivative of this, but if I can break it up into a smaller, simpler piece, then that's going to be very, very helpful. So here's what partial fraction composition says. If I have a rational function, and if I can factor the denominator, which, by the way, in number one is already given to me factored, then this will equal some number over the first factor plus another number over the second factor. Now, what those numbers are, I don't know yet, but this is a true statement. This is a true statement for any x value, right? That if I take this fraction and break it up into little pieces that are whose little fractions are whose denominators of the little fractions are factors of the original one, then I can add those two together and get an answer, and get this answer specifically. Great. So we're always going to start this way. We're going to take the factors of the denominator and we're going to make a little fraction for each of the factors. Now, at this point, I want to figure out what the value of A is and what the value of B is. And so what I'm going to do is I'm going to multiply by the denominator, which in essence is going to eliminate the fraction setup, right? Now, when I multiply on this side, I mean multiply both of these, right? I need to multiply all of this and all of this by the denominator. Why? Because I know these are going to reduce out, and I'm left with 1. And on the other side, I got to be careful. I'm multiplying this times this first, and then I'm multiplying this times this. So let's do the pink line, underlined ones. Well, I'm going to multiply this times this. The x minus 1s are going to cancel, so I'm left with a times x plus 2. Plus, when I multiply these two, the x plus 2s are going to cancel, and I'm left with b times x minus 1. So what happened? I got rid of my fractions, right? My denominators are gone. But here's how we're going to use this idea. We said that this was true for any x value. So what we're going to do is we're going to select a very specific x value to substitute in here. Specifically, I'm going to choose a value like 1 so that I can eliminate one of these factors. So if I choose 1, then what that means is I'm going to substitute a 1 here, plus b times 1 minus 1, and I'm going to substitute a 1 here. right? If my x is 1, then this is going to happen. Well, that's going to eliminate this because 1 minus 1 is 0, and 0 times b is gone. And I'm left with 1 equals a times 3. And if I divide both sides by 3, I get a is 1/3. I just figured out the numerator that goes here. But that's because I used this value. What if I use another value like x equals -2? Then I'm going to have 1 equals a times -2 plus 2, and then let me put the -2 in here, plus b times -2 minus 1, and I'll put the -2 in here. Well, this part is going to cancel out because that plus that is 0 times a, all of that's gone. And so I'm left with 1 equals b times -2 minus 1, that's -3. And if I divide both sides by -3, I'm going to get that the b value is a -1/3. I found this value. Okay, what was the purpose of that? Well, I wanted to rewrite my original integral, and now I can, because we said this integrand, this setup, is equal to the sum of these two little fractions. And so I have the integral of 1/3 x minus 1. Let me write that a little bit clearer. 1/3 x minus 1 plus -1/3 over x plus 2 dx. Well, I can split these up into two different integrals. And I can also push this 1/3 to the front. And I can push this minus 1/3 to the front. Don't forget that when you push it, the x plus 2 is still in the denominator, so I have these little fractions. Oh, but look, I can use like a little u substitution. What if u is x minus 1? That means du is equal to dx. And I can rewrite this. And it turns out that this is going to give me 1/3 natural log of the absolute value of x minus 1. I got this by using u substitution. I'm not showing that. Minus 1/3. Hey, I can do another little u substitution. What if u is x plus 2? Then du is dx. And I do the substitution and I get 1 over u du. Take the antiderivative, and the antiderivative is going to be the natural log of u, which is the natural log of the absolute value of x plus 2, plus c, and I have my answer. All right, that was a lot. But partial fractions is what's going to allow us to take a complicated looking fraction and break it up into little pieces. That's why they're called partial fractions, whose antiderivatives are going to be a little bit easier to find. Remember that whenever the derivative of the denominator is in the numerator, that's going to be a u substitution that's going to produce the natural log antiderivative. We'll do more of these, and the more we do, the more you'll see it's going to be a pretty standard process to do.